this problem. Okay, as you can see, we have a certain force F here applied at D near the end of 380 millimeter lever shown in figure, which is quite similar to a socket wrench, right? Results in certain stresses in the cantilevered bar OABC. This bar, made from this steel alloy and forged and heat treated so that it has a minimum yielding strength of 560 megapascal. Okay. We presume that this component would be of no value after yielding. Thus, the force F required to initiate yielding can be regarded as the strength of the component part. So we need to find this force. That means we need to force that which cause that yielding is that the stress in this range reach to this yielding strength. Okay, I will repeat one more time. We have to find a force that cause a stress in any part of this range result into this yielding strength, which is 560 megapascal. First of all, I have to see where is the critical location that is possible to reach this yielding strength earlier than any other parts. That means when I increase the load from 0 to a specific value, one location at this range, the stress at this location will reach to this yielding strength earlier than others part, and we call that location the most critical location. Okay, so as you can see, at this area we have two diameters. One diameter from O to A is 40 millimeter, and from A to B is 25 millimeter. We know that maximum moment is at point A and equals to F times distance from C to O. And the moment at point A is F times distance again from C but to A. Okay, although moment at A is a bit smaller than O, but as you can see, the diameter at A is much smaller than O. So we can say that, or we can say probably, the maximum stress at this range will cause or will happen at point A, because the difference of the moment at A to O is just very little, but the difference of the diameters are too much. Almost half the diameter at this location is almost half of the diameter from A to O. So I would say that probably the maximum stress will cause at point A. If we later on, if we have doubt about this statement, we can also find the stress at point O to make sure about that. Okay, so let's continue to the solution. So due to this statement that I mentioned now, I will find the value of the moment and torque at point A. Okay, so as I mentioned earlier, the the moment at point A is F times this distance, right? So A times 0.3 meter plus 0.05, and then we will write moment at A in terms of F, 0.35 F. And then we want to find the torque at this value, which is F times this distance, which is 380 millimeter. So F times 0.38 meter. Okay. After we find this moment and torque at this location, now I can find the bending stress and torsional shear stress. Again, we have this equation to find the bending stress at this location. We found earlier MA, so I will substitute, sorry, I have found moment at point A, so I will substitute here, and we have substituted the second moment of area for circular cross section, and then we simplified the equation in this way. And as I mentioned earlier, the diameter of this location is 25 millimeter. I will convert it to meter and substitute here. So the bending stress in terms of F equals to this. In the next step, uh, let me add some point here. As we know that the bending stress at the top of the shaft is maximum, at the center or neutral plane is 0. So actually since we are going to find the maximum stress, so I'm looking the value of the bending stress and torsional stress at the top of the shaft at location A. So because this shaft will bend in this way, so sigma x, sorry, the bending stress in the direction of x and torsional shear stress will be in the direction of z, or tau x z. As you know, x indicates the normal axis or normal vertex, and z shows the direction of torsional shear stress. So by using this equation, again I will substitute J, the second polar moment of area, for circular cross section, and I will substitute the equation in this way. Later on I can substitute the torque at location A we found earlier instead of T, and then we will find tau xz in terms of F. Okay. In the next step, I have to find the force which caused the yielding at the range. To predict the fracture of this material, the material of the range, I have to use one of the theories, one of the appropriate theories for this problem. So let's go to the flowchart that we had here. As we know, this material is ductile. I think it mentioned here. So as you see, this material is a steel alloy and it's a ductile material. So but for the ductile material, as you know, if the yielding point at tension and compression are equal, so we can use either distortion energy theory or maximum shear stress theory. But I'm going to find the answer by using both of these theories. Okay, firstly I will use distortion energy theory. To use the distortion energy theory, firstly I need to find the effective stress or one misses stress. To avoid of finding principal stress first directly, I can use this equation. So the only actual stress that we had was sigma x. Other two actual stresses are 0. So I can assume that this is a plane stress problem, and in plane of xz, and sigma z also is 0, and then tau xz will be substituted here, and we will find a prime stress in terms of f value again. To find the minimum load which causes yielding at the range, the safety factor has to be assumed as 1. So if we consider safety factor equals to 1, we will find the minimum force which causes yielding at the range or in the material. So when I substitute safety factor 1, that means sigma prime should be equal to yielding a strength of material which is 560 megapascal. So sigma prime equals to 560 megapascal, and we will conclude that F, or the force, equals to 1787 Newton. Okay. For the second attempt, this time I would like to find I would like to find F by using maximum shear stress theory. Okay, so here I can use Morse-Tickle theory to find the two principal stress. As you can see, one of the principal stress is positive, another one is negative. That means we have a second case. Let me review how we should find the maximum shear stress when we have one positive and one negative principal stress. Let's say this is sigma A and this one is sigma B. So the next sigma, the third principal stress is 0, and then I have one circle here. I will have one circle here and another one here. So the maximum shear stress is the radius of the biggest or red colored circle, which is sigma A minus sigma B divided by 2. Okay, so we will find maximum shear stress by using this equation. And as you know, shear stress at bending or the yielding shear stress is half of the yielding stress. Okay, so if I substitute 1 for the safety factor, we can simplify the equation that Sy should be equals to sigma A minus sigma B. Sy should be equal to sigma A minus sigma B. And then we will substitute Sy here, the yielding strength, and this result sigma A minus sigma B here. And we will find that F load is 1662 newton. Okay, there is a conclusion or remarks here. If we compare these two values, 1787, let me write here, 1787 by using distortion energy theory. Okay, another one we had this by using maximum shear stress theory. If I compare these two values, we can see that the load caused to load which caused to yielding by prediction of maximum shear stress theory is lower than distortion energy theory. I can write in this way, MSS is lower than FDE. The reason is that, as I showed earlier, the maximum shear stress theory is more conservative compared to distortion energy theory. That means it will predict the failure of the material earlier than distortion energy theory. So that means, or it will say that the material which will fail at the load smaller than the load by using distortion energy theory. That means maximum shear stress theory saying that the material will fail at this load, which is lower than this load predicted by distortion energy theory. That's why we call maximum shear stress theory conservative theory, which predict the failure earlier than distortion energy theory. Okay, so here is the end of